So I have to begin with an apology, and that is I have to leave at 1:30, come rain or come shine, to fly to New York for my brother's wedding. And the second apology has to do, well, not so much an apology, it's just a notification. This is a work in progress, very much. I've only recently become, and by recently I mean within the last month or so, very acquainted with quantum gravity. My primary interest is non-relativistic quantum mechanics, and specifically decoherence, qua physical process and not qua an interpretation or approach or anything else that it gets called. But what struck me many times in the last couple of months is just that there's a really important dynamical story to be told using decoherence, and I think it can really easily and fruitfully be employed in several approaches, but I'm going to give one example, tentatively, where decoherence might have something to say with respect to loop quantum gravity. And then I will leave lots of time for discussion, as per suggestion, so that we can talk, and by we, I mean you amongst yourselves, and I will be happy to listen, about whether or not this suggestion of mine has some legs. All right, so like I said, I began working in non-relativistic quantum mechanics on decoherence. And in particular, let me just start by defining decoherence. I guess maybe that's not something that's done a lot. So quantum decoherence I will understand just to be a physical process, a dynamical process that results from the interaction, the inevitable and in most cases irreversible interaction between some system, however you wish to define it, and some environment, also rather weakly defined. So for instance, you can have entanglement between different sets of degrees of freedom within a single particle, so an electron might become self-entangled, its spin degrees of freedom might couple with its translational degrees of freedom, and you get decoherence there. So what happens is we have entanglement between system and environment. The result of this entanglement is the decoherence, or the smearing out of phase relations within the basis in which the decoherence is occurring. And the result of that is further entanglement, and what I claim to be the appearance of classical or quasi-classical states of affairs. I'm going to fill that all in, don't worry. I want to start with a caveat, though. Decoherence is not an interpretation, it's just this physical process. It gets used by a lot of persons who are involved in the interpretation debate, which I hope to be considered a neutral bystander to some degree, because it might have something interesting to say for various approaches, but it isn't a part of the Everettian approach, and it isn't a part of collapse approaches in any significant way. It may be useful for them, but it is not a part of them. I want to say something else about the measurement problem. I think, and this is sort of methodological, I think a lot of good philosophical work has sort of stopped at the question of interpretation and the question of the measurement problem. And I am here today, at least partly, to give proof that good work can be done, I think, by sort of stepping aside from those problems. Namely, if we look at the dynamics themselves, the physics itself, with making a single choice between two very broad classes of interpretation, we can go on from there and not really think about the interpretation problem, so to speak, and we can do a lot of interesting philosophical and physical sorts of things. So in particular, if you want to think about the measurement problem as the problem of why we don't see superpositions all over the place, well, decoherence answers that, right? Because decoherence is saying that any system which is inevitably immersed in some environment is already decohered to such a state that those interference terms existing between components of the superposition of various states, those are damped or suppressed to such a degree that in most cases when we're dealing with larger systems, i.e. something the size of a molecule, we would have to measure that system for many lifetimes of the universe before we would ever measure one of these suppressed sort of weirdo superposition states. We don't see them not because they aren't there, but because they've been suppressed.
Yes.
You're
not suppressing the superpositions, you're already suppressing the interference.
No, it's the phase relations existing between them, yes. But what that does...
is still there.
That's exactly... Yes, okay, they're still there, right. That's the main point.
Even apart from not being still there, do decoherence has not selected one component out of the improper mix.
Yes, so you're getting ahead of me, but I thank you for that. Right, so if...
For a moment you felt that the job was done by decoherence.
Oh, no. It's yes, no. I want to say that there are various aspects of it that decoherence does have something to say about, but what we might distill as the specific problem of outcomes, Max Schlosshauer defines it that way, and I like it. That still remains unsolved. So, yeah.
Just a quick question. You also talked about measurements. When I measure this or that, I don't see interference.
You can define measurements so weakly that it has to do with exchange of information. All we need is a quantum interaction of some sort. Doesn't have to be a measurement.
But you said that you don't see the interference effects when you measure.
I was being colloquial.
So can you not be colloquial in explaining what you mean by that statement?
Okay, what is it exactly you want to understand why the interference terms are suppressed?
Yeah, for example.
Okay, so that's in the details of the decoherence, right? So what happens when you have the entanglement is that the Hamiltonian, the interaction Hamiltonian for the system in the environment commutes in certain bases, right? Commutes according to certain variables. Those variables, the environment then acts as sort of monitoring. It becomes the measurer, if you will, and it sort of...
So you get an entangled state between the system and the environment?
You get an entangled state between the system and the environment, right? And then those bases in which the system and environment commute, you have a suppression of interference in those bases. So when you're talking about macroscopic objects, decoherence happens extraordinarily rapidly in the position basis, because that's the basis that is commuting most robustly with the environment, if you will. And so all the sort of weirdo, smeared out space-time states that might still exist somehow, insert your favorite ontology, are still there. It's just we can't, in any practical instance, measure those because they've been so damped.
You again use measurement. So what do you mean by that measurement? Is there a collapse involved when you measure at that point or not?
No, so what we have in I don't want to get too sidetracked on this stuff because my point is that we can go beyond this stuff and still say some interesting things, but I recognize that it takes a lot of work to play that apologetic game. I want to brush that aside for the moment, if you'll allow me, and say something more about quantum gravity. But we can come back to that discussion. But to finish the measurement problem issue, we can explain, as I tried to do a little bit just in that comment, about why we get preferred bases, like position for macroscopic objects, or energy eigenbases for, say, the hydrogen atom. So here's a little historical thing, because, hey, I'm HPS. It's the 100th anniversary of Bohr's atom this year. And in recognition, is it still 2013? It is, yeah. Okay. It's been a long... Bohr's atomic model assumes that we have discrete jumps between energy levels, just like the planetary system. We're all familiar with this. Well, planets don't jump, you know what I mean. The electron that's orbiting the nucleus jumps from various energy levels. The reason that we got away with this model, the reason that this model was explanatory successful in certain ways, is because the energy of that electron should be, I mean, in many cases ought to be measured in some superposition of energy eigenstates. But that's not what we get. We measure it in discrete states. We don't get these weirdo energies. That's because it's the electron, before we even come to do any experiments on it, or whatever it is we wish to do with the electron, it has become coupled to the EM field, and it's become coupled also to the nucleus. And so in these various ways, we have an already decohered system. So when we come to measurement, or measure it, however you wish to define measurement, we find it in energy eigenstate. Okay? And again, that's because the interaction Hamiltonian we're discussing in this system environment situation commutes in the energy basis most robustly. Okay, so the question of definite outcomes. I want to say that the reason we think we see definite outcomes is because these weirdo macroscopic states are being suppressed prodigiously by the warm, noisy environment that our lab is immersed in. And this, This means that the decoherence process picks out a basis, an eigenbasis for us in some way. It tells us that we can choose between dead cat and live cat, but it doesn't say why we get live cat in one instance or dead cat in another. It doesn't tell us why we measure x prime instead of x double prime, but it does tell us that unless we waited for many lifetimes of the universe, we're going to get something that's an eigenstate. Right? Are we okay so far? Okay. Not really, but I'm going to go on for the moment. So in that way, the measurement problem has something to, is somewhat dissolved by the decoherence process, but this final question of the specific outcome is not, in fact, answered by decoherence, nor, as an editorial comment, do I think we need that, because I think what it means to really accept that we live in an indeterministic world in this deep way is that we shouldn't expect to find a story that's maybe causally satisfactory that tells us why we get particular x prime instead of x double prime or something like that. But I'm willing to argue with people afterwards, and by that I mean I won't. I'll be on a taxi to O'Hare Airport, so that's my prerogative to just inspire.
Live blogging.
Oh, live blogging, that's right. Daniel is probably taking me to task in real time. Okay. Isn't technology neat? Note absence of slides. Okay. All right, I want to go on and talk about some work that Kiefer and Jost did in 1998, and it was published in 2000. It was part of a decoherence seminar. And as far as I know, they were among the first to really think about what decoherence might have to say about the gravitational field. Namely, why if we expect a quantumly fundamental world, do we have this emergence of classical space-time? And the idea is pretty simple. If we consider the gravitational field, and keep in mind that as long as the superposition principle is valid at all scales, what we're saying about decoherence doesn't have to do with just the Planck scale or whatever. Like, it really is across the board. We're going to get decoherence effects, so it's not something that pertains to different regimes or domains or scales, as it were. It's ubiquitous in an interesting way. All right, so the general idea is when we're looking at the gravitational field, various field strengths in our metric exist in a superposition of the state of that metric. Okay. What happens is we send a massive particle through that metric, through that field. It couples with the metric, and because it's the trajectory of the particle that's coupling to the metric, we get decoherence of field strength. So instead of measuring superpositions of field strength, we get we see the particle traveling through what looks like a quasi-classical trajectory.
What's the environment in that case?
The environment, or the measuring apparatus, or whatever that's seeing or monitoring the field, is this massive particle.
So you're going to trace over the degrees of freedom of the particle?
Yeah, I mean, if you want to talk about it in terms of the reduced density matrix formalism, right, what you're doing is you're tracing over the degrees of freedom of the particle, so we're left with the gravitational field. Exactly. By the way, I'm glad you brought up the matrix formalism. So I think that I realize that the Feynman path integral is sexy and useful for a lot of what y'all do, but it also obscures ontology in an interesting way, because you're summing over all these trajectories, and what does that even mean? What's a trajectory, and what does it mean to sum over all these trajectories? Philosophers get sort of scared by all that. So there's a reason maybe that if we think about alternate approaches to the formalism in terms of maybe reduced density matrices and so forth, we can track our ontology, or at least track what's not allowable in our ontology in a way that's maybe a little clearer. Anyway, that's a philosopher pontificating. Okay, so this corresponds very nicely to something that Christian just said, namely, in loop quantum gravity, we end up via the processes of first quantizing and then constraining our dynamics, is that we get a Hilbert space that's spin network basis, right? That is a spin network basis. And these networks are our eigenstates, right? And the problem that was posed there was that we have this weirdo, non-geometrically realistic-looking thing because we have superpositions of all these network eigenstates. And I think David will possibly say more about this, and possibly more physically appropriately. But decoherence will give us a reason to look at just sort of emergent quasi-classical aspects of those superpositions. So again, we can recover well-defined geometric properties if we allow that these spin networks are in fact immersed in an environment that will cause them to decohere in this basis, in this Hilbert basis. So I've nearly said everything I need to say. How are we doing?
We've got about 20 minutes for halfway left.
Great, so we have lots of time to argue about stuff. I want to say one more thing, and this is just sort of again, sort of methodological, but we heard some interesting talks yesterday and in some of the reading that it's Bose-Einstein condensates and some of the work that's done in solid-state physics that give us some hope, maybe that's a way to say it, give us some hope that we can get an emergent metric of the appropriate sort, i.e. one that we can assign physical reality to in some way, or observables working in that state. But in those discussions, it breaks down, or at least our hope might break down a little bit, because with Bose-Einstein condensates in particular, the metric that we get out doesn't obey general relativistic dynamics. Big problem, right? But in this case, we have an explanation of the emergence of a 3 metric that is physical and does obey general relativist constraints because we built it to do so in the loop quantum gravity approach. One real quick other suggestion about how decoherence processes might have something interesting to say, I'm guessing, in loop quantum gravity, is just that the Ravellian-Smolin, so I just don't know this, their 1990 paper, is that outmoded, or is it still considered like pretty basic? The 1990 Smolin and Rivoli. Anyone? This is where I'm learning my loop quantum gravity
They're
from.
not exclusive alternatives.
So it's
Basic and outmoded are compatible.
it's still very much valid and important, but
Good,
it's 23
okay.
years ago.
Right, of course, I realize this.
I don't understand what is the environment in which these networks live, because these things are supposed to be space-time, or space, and eventually time will evolve from there. So what is out there that is not space-time that acts as environment for these networks?
Yeah, that's a good question. That's something I want to talk about with you, because really, as I understand it, you can define the environment so weakly because decoherence is such an effective process. In many cases, it takes a single scattering event when you're talking about physical objects already. So when we move to this a little bit more abstract, we're talking about different metrics. It could be different metrics superposed on top of each other, that one acts as an environment for the other. It could be that this is one of the suggestions that Kiefer makes, for instance. But I want to ask, I mean, really all you need to do, decoherence shows us in some way that the way you cord off certain degrees of freedom from others is largely just up to us and to our convenience, i.e. what has come to be known as a classical observable is that which was most robust with respect to environmental interactions and so most easily and most repeatedly measurable. If we lived in some other world, perhaps we would not have found position to be, I mean, if all of us were the size of little C70 molecules or something, perhaps we would not find that the most useful or robust observables would be the ones we call classical. But in that sense, what you call your system of interest versus the environment really is almost entirely arbitrary. As long as you can say that these degrees of freedom quantumly interact with these other degrees of freedom, you will get entanglement unless you wish to change the Schrödinger equation.
So do we want to claim that the emergence of classicality is somehow related to our own presence here to select the
No, that's not my claim. That was just sort of an illustrative example.
I think the claim should be that there's no external environment with respect to which this decoherence.
There doesn't need to be an external
That's right.
environment.
It's not to be an external.
Right.
It's degrees of freedom which really are part.
So this is what
That's up to you to divide your system, and you're going to say classicality emerges out of how you decide to divide your system.
That would be a bit of a simplification, right? So, I mean, remember the example I gave of self-entanglements, right? So here we have what we would consider a single system, i.e. a single electron, that decoheres its spin states.
Decoheres if you trace over some degree of freedom, but it doesn't decohere at all if you decide to look at the full picture. So you're going to say that classicality emerges only because I happen to look at half of the picture.
No.
Sorry.
We can say that given that we live in a matter and gravity, like a universe with matter in it, and if we don't want to play the game where we're dealing with the abstract algebra, if you want to think about it as a physically intuitive, conceptual way, or maybe you want to call it naive, whatever. I'm starting from a point of view where there already is matter, so things already are decohered in a certain way.
No, things are
and
not
now, what you call
things are only
classical...
decoherent if you decide to ignore certain degrees of freedom.
No.
Things are not decoherent by themselves.
Yes, they certainly are. Yeah, Jeremy.
Well, I'm trying to, let me try and bring some peace by...
Oh, good. Please do.
You Elise,
That's why we invited you, Jeremy.
I'm agreeing with you in spirit, but not quite in letter, because I think you are tending to speak of decoherence as physically significant, but always there when there's interaction. But I think it's fairer to say that in any quantum theory, either yesterday is an established or prospective for quantum gravity, there's bound to be, of course, a composite system whose state space can be factorized in ever so many ways according to the skill or interest of the physicist. The point about decoherence is not that, so to speak, factorize as you like, interactions are rapid and ubiquitous. It's that, as it so happens, and this was something that Mott and the founding fathers were pretty much aware of, but it became a big thing in the last 30 years, when you model systems that we typically pick out, the detailed physics of how they interact with their environment makes it true that the improper mixture, reduced state of the system very rapidly becomes nearly diagonal in the quantities we love to be definite. Now that's the point. There's always interaction, and you can always reduce and trace out what you have chosen to call the environment.
That's right.
But what matters is the discovery of the rapidity and ubiquity with which, for many sorts of systems, the quantities that we used to love to be definite are nearly diagonal. Are nearly definite.
Are effectively diagonal.
Yeah, right. That's what matters.
Yes, I agree with you entirely.
Right, and there's no reason to think that that's not going to work.
No, absolutely. So if you wish to make the matter the environment of the gravitational field, then indeed you'll get diagonality in the net.
My point is that the situation that you are describing, which is very correctly described what you said, in the lab situation, in which I have a measuring apparatus, macroscopic measuring apparatus, whose states I'm going to consider, and in which I have a particular small system that is a quantum system that I want to consider, all what you have said is true. But here we are in a different situation. We are in a situation we have no apparatuses, no human beings, nobody trying to concentrate and define what are the particular systems that we love. So until one finds out how to divide your system into subsystem and system of interest in a more canonical way, I would have to think that the reality that the emergence of classicality that is being talked about is one that depends very much on this arbitrary choice, which is not preselected by your big apparatus and laboratory measurement. I think we cannot play by the same rules in the two very different cases.
I think I mean, and I want to say that part of what can be said thinking about decoherence is this process, and understanding both your definition of system and environment rather weakly, is that what counts as your measuring device in these instances is the environment, and the environment is everything but the system you're considering.
But I'm considering the whole universe, for instance.
Well, if you're considering the whole universe, then you don't need to worry, because the whole universe is a properly closed system. But can you actually talk about that?
How do I talk about emergence of reality in this universe? The emergence of classicality in this universe?
So here's the thing. I don't believe there is a classical space-time. I'm just trying to explain why we have a phenomenology of it, and why we seem to get measurements in various ways when we do our experiments that seem to lead us to believe that there's a classical space-time metric undergirding whatever it is we're doing, right? I can say that no.
Measurements are playing a very important role in your...
But Luke, quantum gravity, right? I'm explaining, like, there's a truly quantized, the ontically robust something.
Which you cannot understand anything about without your invocation of measurement, which we don't know what it is.
No. Anyway, we can fight about this afterwards. Sure. Tom?
So yeah, I'm kind of on board with this idea that maybe we can separate the matter degrees of freedom and spatial degrees of freedom, spatial temporal degrees of freedom somehow, and that's going to introduce potentially decoherence effects. But I'm just not sure how we're going to define these effects, because the models we have are generally in ordinary non-relativistic quantum mechanics We define a Hamiltonian with an interaction term. We consider unitary evolution with respect to the Hamiltonian, and then, lo and behold, we find that certain observables are somehow picked out as dynamically preferred. But it's just very hard for me to conceive of how that might work in a loop quantum gravity space-time where we're not even sure in what direction time is or how to define the Schrodinger equation and so on.
That's why this is a work in progress.
Well, I
just have this deep hunch that it might be a really fascinating way to go, but you're right. I mean, I haven't figured that out.
Well, in that case, let me offer a suggestion.
Good.
Have you read these ideas about temporal decoherence? So Bianca mentioned earlier these bounds we might have on the accuracy of our clocks. And so if clocks are all we have, then when you write out the dynamics in terms of an imperfect clock rather than the ideal time parameter, you find that coherent states, according to your clock, rapidly decohere into states in which you can no longer perceive the coherence because the inaccuracies.
Yeah, I like that. Yeah. Where's Ben? Oh, what do you think about that?
Is it Gambini and Pulli?
Yeah, yes, that idea. Yeah.
I mean, I have just this comment why so far loop quantum gravity doesn't seem to be. I don't see something particular about loop quantum gravity. It seems to be.
That was just one example from the canonical quantum gravity. I mean, I suppose that any of these. I think that for anybody who wants to talk about emergence of a classical space-time, this might be a route to go. But in particular, I think those approaches that. The canonical approaches, because of the order in which they quantize and then impose the constraints, it makes more sense to me metaphysically to sort of think about decoherence and those within that subset of approaches. And again, that's just a hunch I have at this point in time. But there's nothing to say that this process of decoherence might not have, might not provide physical justification for adopting certain physical bases or for explaining why we're dealing with a reduced Hilbert space in certain algebraic constructions.
One should be a bit careful because we have these kinematic states, which are the spin networks.
Yeah.
And then we have the physical states. And we don't really know whether it's not a given spin network.
Right.
You know, it might be completely very fractal or kind of superposition of very many spin networks or whatever. So.
But even if it is a superposition of many spin networks, we can say, using this dynamics, that what will be the effective. We can say what will be the effective, which ones will be effective. Yeah?
There are many other physical systems where you have some quantum dynamics, and then you get macroscopic occupation that leads to some classical background. The Higgs mechanism for symmetry breaking, Bose-Einstein condensates, chiral symmetry breaking into strong interactions. I've never heard decoherence invoked in any of those as a necessary ingredient to understand why you get a classical background. So is there some reason why loop quantum gravity should behave in a much different way than any of these other quantum systems and requiring decoherence in order to...
I think all of those systems can be given a good story using decoherence. I just, I've been kind of busy. But in all fairness, I really do believe
my
that...
My complaint wasn't that you haven't given a story, it's that there seems to be a perfectly consistent story.
Because I would argue those aren't that they aren't... Right, I would say that a lot of those stories are choosing to interpret decoherence in a particular way, or inputting certain ontological assumptions, like you do have a physical actual collapse at some point, or you do have, you are going to assign what kind of reality you think these these components of the superposition have, whether that be Everettian on a various scale or something like that. Or, most working physicists that I know at least just assume a collapse of some sort, because that gets you the dynamics you need to carry on and do your physics. But if you're interested in metaphysical projects, as I am, there really is a fact of the matter, I believe, for most of the rest of us who don't belong to the collapse theorists, and I think that's a significant number. We want to know why there are interference effects when we why these superpositions seem to physically manifest themselves at certain scales. I mean, there's all kinds of great experiments where we do recover these weirdo quantum evolutions for macroscopic or mesoscopic states. I mean, Hirosh won the Nobel Prize in Physics 2 years ago for Schrödinger kittens, which is exactly a decoherent process. Yeah.
I think if I heard Jeff Harvey's question correctly, there's an option that you didn't accept and should do in his question, and that is classicality, which is not dynamically induced. That is to say, superselection, or the existence of observables that commute with all others, or a classical background. That was Jeff's word. I don't know those advanced physics examples that he cited in his list, but you'd be nuts to say, if I set aside the collapse of the wave function, which you say you don't believe in, which is fine, you would be nuts to say that setting aside the collapse of the wave function, the only way to have classicality in a quantum universe is by the dynamics being such that it gives us the quantities that are normally identified in the decoherence literature. I mean, there's plenty of option to have super selection in a quantum theory. Jeff, did you have sort of super selection in mind? That is to say, classicality that is there by postulate without dynamical induction of it?
No, I don't think I did.
Is the idea that you can avoid being a quantum fundamentalist? Because then maybe I'm talking to the wrong choir or preaching, whatever.
Well, I don't know what a fundamentalist is.
Somebody who believes, I would categorize it as a person who really believes that it all comes down to quantum. Like there's no such thing as an ontologically distinct classical rule that imposes super selection rules. And part of my motivation for being a fundamentalist of that sort is that I think I can give pretty darn good explanations of super selection rules in many cases. Boy, I sound important, don't I? No, I think there's something to be told there that hasn't been told yet. I have this suspicion, and it's because I believe, I mean, sorry, go on.
Well, just that, why not allow that there could be super selection that is not some sort of corollary of what forces are involved in governing things' interaction? There's plenty of scope for quantum theory to postulate super-selecting observables. I mean, the 81 Zurich paper is called environmentally induced super-selection.
Right.
Super-selection is a more general concept. There's plenty of it in quantum theory.
Sure.
But yeah, decoherence is great, but it doesn't have to mop up every example of we find in the quantum universe of super-selection. There's no need to underpin super selection every time by some story of it being dynamically induced between system and environment. So,
I don't know. I sort of think there is. I mean, I agree with you to the extent that I don't think we need a story that picks out the specific outcomes of those selections, right? But that we're dealing with a restricted set instead of the full set of allowable given our formalisms. I want to say that there's something interesting to be told there. I don't know that I have any. I'm not trying to. I didn't set out to undergird these things. I set out because I believe that quantum was the most fundamental theory, and that there was this interesting dynamical process involved in it that does do quite a bit of heavy lifting when it comes to explaining ion selection and so forth. And I suspect that, I mean, if you're okay having something that is a distinct reality from the quantum mechanical and that gives you these superposition rules, okay, then I guess I'm not talking to you as much. I'm talking to those who wish to be committed to and explain everything in terms of quantum dynamics.
Well, we are out of time at this point, and we'll probably end later. Thank you, Elise.
Thank you.